Hello everybody. We're continuing in Chapter 6. This is Presentation C, the third one in Chapter 6. And as we stated earlier, we're breaking Chapter 6 up into multiple presentations so we can go into a lot more detail about testing procedures that are covered in this chapter. So I'm going to be talking about your TSR test, which is primarily a requirement for your mix design technician, but now that it's moved to be part of a production sample, we're going to cover it during the asphalt plant level 2 class, and we're going to talk about the moisture content and boil test. Let's start with the TSR test. TSR is a measure of strength loss resulting from damage caused by stripping under laboratory controlled accelerated freeze-thaw conditioning. A whole lot of words there to tell you about that some of these samples are conditioned and you're doing a strength comparison. The test procedure we follow to run the TSR test is AASHTO T283. This test method is used to determine if the material, when I say material, I'm talking about the aggregate and the binder, may be subject to stripping, and to measure the effectiveness of additives that can help improve stripping potential of these materials. These results can also help predict long-term susceptibility to stripping of an asphalt mixture during its performance in the pavement. The stripping test, as we said already, is to combat the effects of water damage. VDOT does require by specification an antistrep to be used in all mixes. Doesn't matter if it's surface, base, wherever. All asphalt mixes have to include an anti-strip agent. This can be either 1% hydrated lime or any other VDOT approved chemical additive that is on VDOT's approved list. One thing about the TSR test, up until 2018, 2019, TSRs were always done during the mix design phase. At that time, VDOT changed to allowing TSRs to be done on the first lot of each production of a new job mix. Basically, it all happened when we went to a two-part mix design approval. We have a Part A mix design approval and a Part B. Part A is when you turn in your job mix formula, and that basically your starting point that you're allowed to go into production for one lot, 4,000 tons. And during that one lot, you can make any adjustments that may be different from lab-produced mix to plant-produced mix to have your final job mix formula for the remainder of the calendar year. So during this Part B process, you must also do a TSR. The advantage of that is we're running TSRs on actual plant mix versus lab-produced mix. So to prepare our specimens for TSR, as we mentioned, this will be plant mixed lab compacted specimens, and you must produce a minimum of 6 specimens. We highly recommend you do a few more, 8 or even more than 8, and I'll explain why when some things can happen to specimens that you may have to have a backup. There are a couple specimen sizes you can use. You can do a 4-inch diameter, 2.5-inch tall specimen. Those specimens will be made with the Marshall hammer, typically, and they work great. That's used to be all we had before Super Pave was out, was the Marshall hammer, and we made Marshall TSRs. Option 2 is to use your gyratory compactor and make a much larger specimen. It's a 150 millimeter, 6-inch diameter by 95 millimeter tall, or 3.75 inches, 3 3/4 inches tall. So depending on which compactor you're using will influence the size specimen you're going to use. I will say sometimes the larger specimens may be a little harder to saturate just based on volume and size than the smaller specimens. Once we've produced our 8 or so samples, you want to store them at room temperature for 24 hours plus or minus 3 hours. After we've stored them basically for a day, 24 hours, first thing we want to do is measure the height and the diameter of each specimen. Once that's been done, we're going to determine the voids of each specimen. The void content has to be around 7% plus or minus 0.5% air voids. All right, so that's a narrow air void range. As I stated previously, you need a minimum of 6 specimens. Here could be where 1 or 2 specimens can be outside that void range, and you would have to discard them. Once you've measured your voids on all your specimens and you've got everything, your heights measured and your diameter checked and measured, you want to separate them into 2 subsets of at least 3 specimens each. The goal here for these 2 subsets is to have approximately equal air voids in each subset. In other words, I don't want one subset to have all the high voids and the other subset have all the low voids. I want the average of the air voids between the 2 subsets to be somewhat equal. These 2 subsets from going forward will be called a dry subset and a conditioned subset. For the dry subset, pretty simple work for the next day. All we're going to do is store it at room temperature. Put them on a shelf, put them somewhere they won't be damaged. Don't put them on top of an oven where the heat could mess them up, but just set them over to the side and let them set for about a day. Meanwhile, on the conditioned set, which is your other set of specimens, we're going to vacuum saturate each specimen to between 70 and 80% saturation. This saturation is typically done with your same rice setup. You'll use your rice bucket, you put your specimen in your rice bucket, and you'll vacuum saturate it for 3 to 5 minutes or whatever it takes. One word of caution, you want to vacuum saturate at a much lower pressure than we normally run a rice sample at. Also note here that if any specimen is undersaturated, you can resaturate it to get it between 70 and 80%. But if a specimen goes above 80%, it is damaged, and again, the specimen would have to be discarded. That is another reason why we would like to have an extra specimen or 2 from our field production already made, so we can just slide it into this slot and keep going. Once our conditioned specimens are saturated properly, we want to wrap each specimen in saran wrap or some sort of plastic wrap that'll cling to the specimen real well, and place it in a plastic bag containing 10 milliliters of water. Once they're in these bags, we'll place the bag with the specimen in it, sealed up, in a freezer for a minimum of 16 hours. Okay, it can go longer than 16, but it has to be in there for a minimum of 16 hours. At the end of our freeze cycle, we then will take these specimens, we'll pull them out, and we're going to put them in a hot water bath. So you need a hot water bath that's going to be set at 140 degrees Fahrenheit or 60 degrees C, which is quite warm. So you want to pull them out, you want to take them out of the bag, and you want to also take the plastic wrapping off your specimen. So what I recommend is just dunking your specimen real quickly in this hot water. Once that happens, the plastic basically falls off your specimen, and you can just set your specimens in there. So we'll have all 3 specimens in this hot water bath. They'll soak in this hot water bath for 24 hours plus or minus 1 hour. Now we're going to bring back our unconditioned or our dry set and our conditioned subsets back together for the next part of the testing process. At this point, we're going to take the conditioned set, remove them from the hot water bath, and we're going to place them in our typical way bath or in a much cooler bath. It's at 25 degrees Celsius plus or minus 0.5 C, or 77 plus or minus 1. Note that is a plus or minus 1. That is a narrow temperature range that we're trying to keep these specimens in. So we're going to place our hot specimens in there, and at the exact same time we're placing the conditioned specimens that were hot in this bath, we want to add the other 3 specimens, it's the dry subset. But in order to add the dry subset in there, we want them to stay dry throughout the entire process. We don't want them to have any moisture conditioning added to them at all. So these subset specimens must be wrapped in plastic and placed in a leak-proof bag. Then the whole bag is placed in the 77 degree water bath. So basically in this water bath, we will have all 6 specimens at the same time, and 3 of them will be in a bag. The dry set is staying dry the entire process. The conditioned set stays wet the entire process. One thing I do want to note here, when I'm putting a hot specimen, or if you can imagine putting anything hot in a bath that's much cooler than the hot specimen, that heat will dissipate into that water bath and cause that water bath to increase in temperature. it's very important to have a cup of ice, and I don't mean a little coffee cup, I mean a pretty good large mega coffee cup, you might say, of ice ready to dump in your water bath to maintain that temperature, because remember, we're at 77 plus or minus 1 degrees, and it's important to have ice for that water bath to maintain that temperature. Now that we've brought all our specimens to the same temperature, and basically that's what the 77 degree water bath is for temperature equilibrium of both the conditioned set of specimens and the dry set of specimens, we need to go ahead and do our test, which is finally, with all this conditioning cycles we've done for multiple days, we're finally ready to test our specimens. Before we can actually break the specimen or test the specimen, we must first measure the thickness of each specimen. Okay? That's just done with a set of calipers. Once we've done that, then we can determine the tensile strength of each specimen. To do that, basically, once a specimen is broke, the tensile strength we're looking for is the peak pressure that the specimen achieves prior to breaking. And once we've done 6 specimens now, a minimum of 6, you can do more. We're going to have 3 that were conditioned. Our conditioned set of pills were vacuum saturated to between 70 and 80%. They were wrapped in plastic and froze for a minimum of 16 hours. After the 16-hour cycle, they were put in a hot water bath, 140 degrees Fahrenheit, for a minimum of 24 hours. Then after the 24-hour soak, they were done temperature equilibrium for 2 hours in the 77-degree bath. Whereas the dry subset of pills sat on a shelf for those first 2 days, and then all they did was get the temperature equilibrium, but they were kept dry the entire time. So once we've broken each one of these pills, basically we'll take the average of the conditioned set, which is the ones that had all the conditioning, and the average of the dry set, and it's just a ratio, and the requirement for TSR testing is a minimum of 80%. TSR is the typical test used to actually quantify stripping, but another test that's recognized in Virginia and actually was around quite a bit prior to SuperPave was the boil test. Earlier in my career, I worked for VDOT, and we used to run the boil test almost daily because it's a great indicator of possible stripping. So we're going to cover that next in the next few PowerPoint slides here, give you an idea of what the boil test is. Asphalt mixture is subjected to the action of boiling water for a specified period of time to determine the effectiveness of the anistrip that is being used on the mix. Because remember, as I stated earlier, VDOT requires an anistrip on all mixes. All right, this test procedure is Virginia Test Method 13, so you can find it in your Virginia Test Methods. And basically, it predicts short-term aging, or short-term stripping, excuse me. With that said, the reason you don't see this test run a lot is because it's not as direct or absolute as the TSR test. The TSR test, once we're done, we have a quantifiable number. It might be 92, and if that's greater than 80, guess what? It passes stripping TSR test, tensile strength ratio. If it's 72 and it's below 80, it fails. It's very quantifiable and easy to understand. Where when it comes to the boil test, this is basically a pass-fail, and can be some discussion about the interpretation of what pass and fail means. I'll explain more as we go through this. To start with, we're only going to deal with the material that's passing the half-inch sieve. So even if you're running a base mix, an intermediate mix, or a larger sieve size mix, you want to we're only going to boil so that we don't break the beaker, the minus half material. All right, the concept is the same aggregate, whether it's the coarser aggregate, a 25 millimeter or 19 millimeter, would have the same stripping effects as a finer material that you're going to have on a half-inch minus. So we just break it over the half-inch. Okay, then what we need to run this test is 400 grams of weight. We're going to place 200 grams on a paper towel, and that becomes basically our control sample. It's just going to sit there. Nothing will be done with that 200 grams that's on the paper towel. The remaining 200 grams will be placed in boiling water. It's all right. Before I can put my mix in this boiling water, the water must already be boiling. So we don't want to wait for the water to begin boiling. You know the old saying, how long does it take for water to start boiling if you're watching it, you know. But the point is, It goes in this boiling water for 10 minutes plus or minus 30 seconds. One thing I like to tell people when you do run this test, if you do have stripping occurring, the asphalt binder will begin to float on top of the boiling water. If that happens, I recommend you take a paper towel, another paper towel, and dot that material, that floating asphalt out. You just tap the top and it'll stick right to the paper towel and pull it out. Otherwise, when you go to pour the water off and to get your sample out to do your evaluation, that asphalt binder will lay back on the aggregate and it won't be a correct test. All right, so this is where the part where people have different interpretations seems to happen. All right, basically you've got your control set setting here on one paper towel, and the other set, as you can see where the water is, was the set that was boiled for 10 minutes. This 10-minute boil, you have to first allow this specimen to completely dry. You can put a fan in front of it, it'll dry in a couple hours. Once that's done, you then visually look at the two samples and visually compare, did some stripping occurred on the boiled sample, using your unboiled portion as a reference. Okay, if you do see stripping that's occurred, you need to run a second sample as quick as possible. If the second sample again shows that some possible stripping has occurred, you need to cease production and find a corrective action to resolve this process before continuing production. This is the part why I think we don't see this boil test run as much, because it opens it up to interpretation of, do I call this stripping or not? But I will tell you the nice thing about it, we just covered the TSR test, which took 4 days to go from taking my sample to getting a TSR value. I can have a boil test value in a matter of a few hours. It's a great indicator, which may, in a lot of cases, indicate, oh, I might want to pull a TSR when I pull my second test if something's not looking right, because I want to make sure of this. I can also tell you from previous experience, this boil test, another part of my past career was I was with a producer, and I used to make asphalt. And of course, everybody's trying to sell me a new snake oil being a different anastrip additive. This is a quick way to do a screening of the potential of a different anastrip additive on your mix without taking 4 days to do TSRs. This boil test can, if you mix up a sample with one anastrip additive and another sample with a different anastrip additive and run them both through the boil test, you can quantify really quick which one of these is going to work better with your aggregate and your binder. So I always like to mention that to everybody. It's a great tool for that purpose as well. All right, now that we're done talking about stripping, let's talk about moisture content of asphalt mixtures. Moisture content is something we're supposed to be checking on our mixes during production. To do this, we have to obtain a representative sample in accordance with AASHTO R47. Same way we would be splitting out any of our other samples. Typically, you may, if you split out your furnace burn sample, which we talked about in a previous presentation, you may use a different quadrant of this split as your moisture content. All right, to start with, I'm going to have a clean pan. I want to record the weight of a dry, clean pan, okay? Then I want to place this sample that was split out properly in this pan and record the weight of the sample and the pan. Once that's been done, pretty easy test to do, I put this sample in an oven. We typically use a compaction temperature for 90 minutes. At the end of 90 minutes, I'm going to take the pan and sample out and I'm going to weigh it, okay? Once I've weighed that, I'm going to put it back in the oven for 30 minutes and I'm going to take it out and weigh it again. These 30-minute increments will continue until I've achieved a constant weight. From that, I can easily calculate my moisture content of my mix. So here we have a video of a technician. He's weighing his empty pan, 545.8 grams. He's noted that. Now he's getting a weight of his pan and his sample, which is 2,045.5 grams. From here, he's going to place this sample in an oven. I like to point out that he's putting this moisture sample on the top shelf. Moisture will be coming out of this sample, so he wants it to, moisture is going to rise with the heat. He puts it on the top shelf where he gets the best chance to remove the moisture. Now he's checking his sample for his final dry weight. This will be his constant weight. It looks like he had 2,042 grams. From the difference in these weights, he can calculate his moisture content. To calculate the moisture content of his mix, it's a simple formula here. He's got the weight of his wet sample minus the weight of his dry sample, which is simple math here, and he's going to divide it by the weight of his dry sample times 100. This will tell him the times 100 to convert it to a percentage, and this will tell him how much moisture he has in his mixture. There is no specification requirement on moisture for your individual stockpiles when you're in production, but there is a requirement for moisture on your finished mix. The finished mix must have less than 1% moisture. And several people have commented in the past that higher moisture contents in mixes, maybe not as high as 1%, but getting up there close to 1%, may affect the mix's compactability because it can be tender when there's extra moisture in the mix. So it's one of these tests we do want to check periodically, and I do recommend you definitely anytime you have a storm or a full day of rain, the following day when you start up, you want to check this moisture content. Tends to be everybody likes to produce their mixes at the same, 300 tons an hour, and they just want to keep that constant. Well, when rain happens, we may have to slow that down to 200 tons an hour to make sure our mixes have time to dry during the mixing chamber of our production process. So it's important to check these moistures, especially after a rain event. With that being said, we've covered the TSRs, we've covered the Boyle test, and we've covered the moisture, how to measure the moisture content of your mix. There are some knowledge check questions at the end of the chapter, and we appreciate your time.